Very good morning, my dear students. Again, continuation of the last PPT. So, in this class, I'm going to solve the two numerical problems on forced vibration. Okay. So, I told you what you mean by vibration and what you mean by forced vibration and different types of forced vibration in the first introduction class. Okay. So, again, once again, I will tell you what you mean by forced vibration means the vibration takes place with the help of some external applying force within respect to time. Okay. So, that is called as what the forced vibration. Okay. So, here I'm going to solve some more numerical problems. Okay. Different types of problems. That is how we are going to transfer the force from the component that is a mechanical device to the ground level. Okay, such type of problems we are going to solve in this class. Okay, so third problem, so I'm going to read the question now. The third problem, that is a machine of mass 2000 is there. A machine of mass 2000 Newton is mounted on a rubber pad, okay, which gives the initial static deflection of 2 mm under the self weight of a machine. Okay, it is also provided within a damping such that the damping ratio is 0.2. okay, so this is the okay, so one machine is there. Okay, so on machine there is a mass of 2000 Newton is the mass, that is a weight is added on that particular machine, okay, on the rubber pads, okay, which gives an initial, okay, after you apply this force there is it will give some initial that is a deflection. Okay, so that is about 2 mm under the self weight of the machine. Okay, so take any one component, if you apply some loads, it will change the displacement. Okay, that the deflection is 2 mm. It is also provided with a damping such that the damping ratio, that is the damping ratio is equal to what, the zeta, that is a zeta is equal to 0.2 is given. So determine following three factor, that is a resonant frequency and the maximum amplitude and the corresponding frequency, the phase angle at omega is equal to radian per second. Okay, I told you, so before solving the force vibration problem we have the make a list of formulas, okay, and the symbol which what we are going to use. Okay, so here note down the first step is given data. So given data, mass is equal to given 2000 Newton and deflection delta, the deflection is generated by delta is equal to 2 mm and zeta is equal to 0.2 mm, that is the damping ratio is given. Okay, so note on the given data first step. So what they asking, resonant frequency, I given in the list what is the formula, and this is formula and this formula, all three formula I mentioned in the notes. So take the notes and so remember the formulas. Okay, so given data again I wrote here. So resonant frequency at resonance omega is equal to omega, so in the place of it is given in terms of the deflection, so use G by delta. Okay, in place of the given spring mass difference, spring and stiff damper means use mass means K by M. Okay, the given problem is that is the deflection, so omega is equal to omega and square root of G by delta. So G is equal to gravitational force, that is 9.81. Deflection is given, you have to convert this 2 mm into a meter, so divide by 1000 you are going to get 0.02. so if you calculate this you are going to get about 70.03 radian per second. Okay, so this is about the first one. So second one is what, the maximum amplitude. So maximum amplitude is equal to what, x maximum is equal to x of, that is static deflection divided by 2 zeta square root of 1 minus zeta square. Okay, so substitute here all the values. So 0.02002 divided by 2 into 0.2 square root of 1 minus 0.q. Okay, so if you substitute you are going to get the 0.05 meter. Okay, so v peak, that is the angular frequency of the peak is equal to omega n into square root of 1 minus 2 zeta square. Okay, so we have the omega n values and zeta values. Okay, substitute, so you are going to get the omega is peak is equal to 67.17 radian per second. Okay, again the last one, third case one is phase angle at omega is equal to 1000 radian per second. Okay, so we have the formula, this phase angle formula, 2 tan phi is equal to 2 zeta omega by this what, omega n, so whole divided by 1 minus omega by omega n whole square. Okay, so substitute all the values here, so you are going to get phi angle is equal to finally 151.20 degree. Okay, so this is a phase angle. At this angle we are going to get in the machine component. Okay, that what the here they are given what, the phase angle at omega is equal to 1000, that is 100 radian per second. So at this if you substitute their value you are going to get 151, so it means the graph should be goes down direction. Okay, so and this is about the first problem answers. Okay, just you have to remember the formula, list of formulas what I am going to use in the what the forced vibration problem. Okay, so while coming so next problem number 4, a mass of 100 kg been mounted on a spring dashboard system. That means a spring damper system is given, that is a spring is there, mass is there, damper is there. Okay, so 100 mass of kg is mounted on that particular, okay, having a stiffness of this 19,600 Newton per meter and damping coefficient C is equal to what, 100 Newton second per meter. The mass is acted upon by a harmonic force, that is a wave equation force, that is in terms of sine and cos of 39 Newton at the undamped natural frequency of the system. So calculate the following three factor. Okay, that is first is equal to what, amplitude of the vibration of the masses, phase difference between the force and the displacement, and force transmission ratio. Okay, so these are the three factors you need to calculate here. Okay, one spring mass damper system is given, so upon which the mass is acted about 100 kg and damping is 19,000, the spring stiffness is given 19,600 and C is given 100 Newton second. Okay, so again if you operate that, the force going to transmit from the system to the ground level. Okay, that you need to calculate here, that is force transmission ratio. Okay, so the spelling is mistake is there, so N is not there. Okay, so force transmission ratio you need to calculate. Okay, so before solving this, again you note on the given data, that is mass is given 100 kg, stiffness is given 19,600 Newton meter, and the damping is given 100 Newton second per meter, and external force, that is a waveform equation, that is a harmonic force, is equal to 39 Newton. Okay, so these are the given data is given. By using this, you need to calculate the following these three, that is amplitude, phase, force. Okay, so again given data is given mass. Okay, we have the formula, undamped natural frequency is equal to omega n is equal to root k by n, k by m. Okay, in the previous case where we are going to use the j by delta because that is in deflection. Okay, so here omega n is equal to k by m. Okay, so here root k by n is equal to square root of 19,600 divided by 100. So substitute value you are going to get omega n is equal to 14 radian per second. Okay, so if you want to go further calculation, we have some basic you have to calculate, that is critical damping is equal to 2m omega n. Okay, 2m is there, omega n also calculated, substitute you are going to get critical is equal to what, critical damping you are going to get 2800 Newton second per meter. So once we calculate CC, go for damping. So damping is equal to what formula? It is the ratio of damping to the critical damping is called as damping ratio. Okay, so it is also called as the impact ratio also. So C is equal to 100 whole divided by 2800. Okay, substitute, if you substitute this formula, you are going to get damping is equal to 0.0357. Okay, so damping is equal to 0.07. Okay, so first, before solving, after calculating all these quantities, we go for one by one. Okay, that is at the undamped natural frequency omega is equal to omega n. So hence the amplitude of the vibration is given by the maximum amplitude x indicate what, maximum amplitude is equal to f naught by k, that is harmonic force, whole divided by square root of 1 minus omega by omega n square whole square plus 2 zeta omega by omega n whole square. Okay, so once if you calculate, once if you remember this formula, so substitute, we have with us all the values data. Okay, substitute all the values. So you are going to get the maximum amplitude is equal to 0.0278 meter. Okay, so second case is the phase difference. So phase difference is equal to what, at omega angular frequency is equal to that natural frequency, then only we are going to generate the phase difference. Okay, formula we have this in this. Okay, tan phi is equal to 2 zeta omega by omega n whole divided by square root of 1 minus omega by omega n whole square. Okay, so we in the phase difference we know that this omega is equal to omega n. Okay, so if substitute here, so you are going to get cancel, you are going to get the tan phi 2 zeta. Okay, so that become infinity. So tan phi is equal to 90 degree. Okay, a phase angle going to phase difference between the two wave, that is two wave, you are going to get what, the 90 degree. Okay, 180 by 2 90 degree you are going to get. So last one is the force transmissibility ratio. Okay, that is how much force you are going to transmit from the system to the ground level. Okay, that it is shortly denoted by TR. Okay, TR is nothing but what, transmissibility ratio. Okay, transmissibility ratio is defined as what, the force transmitted to the machine to the ground level is called as transmissibility ratio. Okay, so with us we have the formula, this is the transmissibility ratio, and also we are going to calculate this derivation we did in the theory class. Okay, so square formula is what, square root of 1 plus 2 zeta omega by omega n whole square whole divided by square root of 1 minus omega by omega n whole square plus 2 zeta omega by omega n whole square. Okay, substitute all the values here, you are going to get the transmissibility ratio of 14.04. Okay, so this much of amount we are going to transfer the forces from that one component to the another, that is the ground level. Okay, so like this you have to solve the numerical problems on force vibration. Okay, so the main thing to solve the vibration problem, okay, how you are going to solve means you have to remember the list of formulas first. Okay, without formula we cannot solve a single problem on this. Okay, so I have told you number of times notations are very important here in this, especially from the model 4 and model 5. Okay, that is what, zeta means what, it is a damping, k means stiffness, c means damping. Okay, x maximum is equal to maximum amplitude, f naught is equal to what, harmonic. Okay, k is nothing but what, the stiffness, omega is equal to angular speed, this is a natural frequency. Okay, so we have to remember all the list of formulas. Okay, so then only we are going to solve this numerical problems on this forced vibration problem. Okay, so again, so here okay, also this is also very important formula, that is cc is equal to 2m omega n. Okay, sometime you are going to use direct in the equation, that is upcoming problem. Okay, cc nothing but what, critical damping, and only c nothing but what, that damping. Okay, so this is very important, this question they may ask you in the what, in the competitive exam also. Okay, calculate the damping factor anta. So you have to, they may give C and CC, so just substitute, you are going to get this value. Okay, so I hope you understand these two problems. Okay, so nothing is there here, so you have to remember the formulas, that's it. Okay, so main thing in the especially in the model 4 and 5. Okay, so if you remember the formulas means you are going to get the final answer. Okay, now I am going to stop this. Okay, so I hope you understand these two problems. Okay, so practice, take any textbook or reference book, practice. If you have, you can work out as per this procedure. Okay, so I hope you understand this. Thank you.